Welcome to this lecture, Electrophysiology. In today's lecture, we'll be mostly focusing on the following main topics: the resting potential and action potential, uh, the experimental setup to generate action potential, and there is an equation, one of the important equation which is used to calculate the action and resting potential. It's called the GHK equation, and we'll also try to solve some example problems, and in the end, we'll have some discussions. So before we go into the details of the action potentials, we'll be just look at the topic that we have discussed, a quick review of the topic that we discussed last class. So what we have seen last class, we have find out the Nernst equation, and as we all understood the Nernst equation, VNA, or the potential due to the sodium, it is obtained by the equation RT over ZF ln of CI by CE by CI in millivolts. So this is the next equation, which is normally used to find the electrical potential due to difference in ionic concentrations between the intra and extracellular fluids. So if a particular cell which separates into two small cells, and when there is a difference in concentration exists between any kind of ions such as sodium, potassium, chloride, etc., there is a potential is existing, and this potential is normally called as the Nernst potential. And RT bar ZF, RT stands for the gas constant, T is the temperature in absolute Kelvin scale, the temperature in degree Kelvin, and Z is the valency, which is the sodium, which is +1, potassium it is -1, and for sodium and potassium it is +1 and -1 for Cl. Fe stands for the Faraday's constant. Ln is the natural logarithm operator. Ce stands for the concentration of, in this case, Na extracellular concentration of sodium, and Ci stands for the intracellular concentration of sodium, and mostly it is in millimoles. That's the unit. So the end result we are getting in terms of millivolts. Similarly, we can also calculate Vk and Vcl. Accordingly, we just now substitute the corresponding value of the Ce and Ci for potassium and chloride respectively. And if you substitute the value of RT bar F constants, all the constants, then for a temperature of 27 degrees centigrade, then then the value will be equivalent to what equal 26 milli. So in most of our calculations, we are considering is 26 milli. Now the second model that we have discussed is called the parallel conduction model, conductance model, because as you know that we have potassium, sodium, and chloride potentials are there, and this is like we just try to mimic a cell membrane, whereas this is the exterior part of the cell, which is we also call the extracellular site or the extracellular fluid, and this is the intracellular fluid. Because of the difference in concentration between potassium, sodium, and chloride, we expect three Nernst potentials, which are Vk, Vna, and Vcl. And this polarity something is very important. It shows that this potential is negative, this also negative, and this potential is Vna is positive. We are keeping in mind that inside we are assuming that positive inside we are assuming it's negative with respect to outside. So that's the difference. So normally in the case of rest condition, as you know that the potential is negative inside with respect to outside. This Gk, Gna, and Gcl are indicating the conductances. As we said that for the ions to penetrate through these different channels, the channel allow the ions in different way. In having different conductances. For example, in the case of sodium, it can easily pass through the channel, whereas the potassium and chloride having difficult because of their shape and the properties of the channels and so on. So as per this, Gk stands for the conductance of K plus, Gna is the conductance of sodium, and Gcl is the conductance of the chloride ions. Vk, Vna, Vcl are the Nernst potentials due to sodium, potassium, sodium, and chloride respectively. This CME stands for the membrane capacitance. Already we have discussed that the membrane is acting like a capacitance because the material membrane itself is a dielectric, and on either side we have what you call conducting fluids. So two conducting fluids which are separated by a dielectric cell membrane, the whole setup will be something similar to a capacitance, and that capacitance is called the membrane capacitance. And then we proved that at steady state condition there is no flux because there is a balance is achieved between the concentration of the intra and extracellular fluid, and as a result at steady state condition there is no flux, and then we concluded that V rest is equal to Vk Gk plus Vna Gna plus Vcl Gcl divided by Gk plus Gna plus Gacl. So these are the same definitions that we already discussed. So using this equation we will be able to find out, or we can calculate the value of resting potential due to three major ions which are potassium, sodium and chloride. So this point also we have discussed in the last class. Now let's look at what is the action potential. Biological membranes contain large number of several types of ion channels. These interact through their common transmembrane potential and capacitance. A remarkable result is that such electrically active tissue, by means of a regenerative process, can generate transient pulse. What do you mean by transient? Transient means what? It is existing only for a short period of time. So it can generate a transient pulse of electric changes. And action potential, that transient pulse is normally referred to as the action potential. So an action potential that can be generated across the cell membrane. The action potential cycle consisting of rapid membrane depolarization, which means that there is a new potential is generated, for a positive potential is generated, or rising potential is generated, or there is an increase in the transmembrane potential. Normally at rest condition, as we said before, is normally negative. Then because of this action potential, for a very short period of time, the negative potential become positive potential, followed by slower recovery. So you cannot stay in that particular state for a long period of time. It has to come back by a natural phenomenon. So it has got a depolarization process, which means that there is a changeover from negative potential to the positive potential, stay for a very short period of time, then come back by a process called repolarization, where the positive charge or the positive polarity become negative polarity, or this is also called the resting potential. Once the action potential is initiated at one site on an extensive membrane, it initiates action potential at the adjacent sites. So once it is generated at one site, what happens? It may cause the further action potential in the adjacent sites, thus leading to a sequence of action potential throughout the remaining membrane. So it's like a chain reaction. If there is a strong stimulation is applied. Now here we'll show a small model, a model that demonstrates the action potential in a cell. So you can see this is the cellular structure, and here S stands for the stimulator, and here is a voltage source, voltage indicator, voltmeter. So using a stimulator we can stimulate the fiber, the nerve fiber. So normally stimulation we are using current. So let us look at, in this case, this is this indicate the stimulating current source. So you can see that it's very short time what you call pulse of is having certain amount height or certain ampere. Normally in the case of milliamperes, certain amount of current, it is applied across the two terminals of the stimulating electrode. So we are using two stimulating electrodes here, one outside and one inside. Now this will cause some changes on the cell membrane. As a result, the the disturbance happens because there was a balance is achieved before balance is achieved before the action potential, before the stimulation happen, that particular balance is collapsed because of this or is disturbed. As a result, there is some kind of flow will happen because some of the ions may leave the cell and some may enter the from out extracellular fluid to the intracellular fluids and vice versa. So that will rise to a potential here. So we can see that the potential was Vm, which is called a resting potential, and the moment we apply, after taking some time, after a small period of time, that period is normally called as latency. So latency is nothing but the time that is required for an action potential that is to be generated, which or it is starting point of the action potential from the stimulating instant. So from that instant to the onset or the starting point of the action potential, normally called as the latency. So you can see that there is, after a latency period, the potential is become positive. So from negative, the potential rise to positive, and it stays there for a very short period of time, and it drop down to the original potential, which is the resting potential. So the whole process is basically called as the action potential. Now let us see how we can record this action potential from a nerve of nerve or muscle fiber, okay, either from a nerve a fiber or maybe a muscle fiber. So what is required for our experiment? So let us assume that we are trying to experiment on a worm muscle fiber, and in order to stimulate, we are using a stimulating electrode, and in order to record, we are using a recording electrode. So we are using a stimulating electrode on one side, and after a short gap, we are using a recording electrode. Now, in order to stimulate, we are using a stimulator, and normally, as we said before, it is a current source which generates a pulse for a short period of time. Using this, we can stimulate the muscle. So then we are using an oscilloscope to display the output response or the action potential or output waveform or the transmembrane potential, as well as the corresponding the stimulator output as well, the stimulation signal. So stimulating signal as well as the output has to be monitored on an oscilloscope. Then normally the signal that is generated, the action potentials or the transmembrane potential is of the order of millivolts. It's hard to display it on an oscilloscope, so we need a amplifier. So using an amplifier, we can amplify the signal so that can be displayed on a oscilloscope. So now this waveform indicates that there are three levels of waveform. The first waveform indicates that there is no action potential is generated even though a small amount of current is applied, because the important point is here, every muscle fiber has got a specific value or a specific level that is normally called as threshold, and if the stimulating current is below this threshold, then that is not going to cause any kind of action potential. So in this first example, what you can see that the moment we apply a stimulus, of course there is a change in the the shape, but there is no action, there is no rising potential, because the applied current or the stimulating current is well below the threshold. If you see the second one, as the action potential is further, the amount is further increased, and it is once it is crossed the threshold, the action potential is generated. So you can see that there is an action potential is generated here. So the signal, when the moment you apply, you can see there is an action potential is generated. And again, this action potential will stay for a very short period of time, and it return back to the resting. So this line indicate the baseline or the resting potential here. Now the third one indicate that here the amount of stimulation is much larger or sufficiently very high, and as a result this will cause two action potentials or one action potential followed by another action potential. The reason is that if you're considering each individual muscle fiber, depending upon the diameter, the stimulation current varies. So at a lower threshold, probably certain what you call nerve fibers may stimulate, whereas as the current further increases, what happen, more number of muscle fibers, they may get stimulated further. So you may have multiple action potentials. These multiple action potentials generated from different muscle fibers, and their diameters may not be the same. So it normally happen at a very large amount of what I call the stimulating current. We'll explain this detail more. So the observed waveform of the action potential on an oscilloscope will be looking like this. As we said before, the resting potential normally in the range of minus 60 volt. Average will be somewhere around minus 60 volt, and we are going to apply a stimulus well above the threshold limit, and this is the baseline or the zero line. This is not this is basically the zero axis. So you can say this is a negative side and this is supposed to be positive side. So what you can see, the moment you apply, then the voltage will increase and it reach somewhere around plus 40 millivolt, which is above zero. That's why I call positive 40 millivolts, around 40 millivolt, having a peak at here. Then it drops down. Okay, then you have something called, before it reach the resting potential, there are some ups and downs, and finally it reach the steady state point here. So this is a transient phenomenon here, and the level above the zero level normally called as the overshoot. So the gap from the zero until the peak point, that's normally called as the overshoot here. So this phase is normally called as a rising phase, where the voltage is increasing, and this is called the falling phase. And of course, there are a lot of ups and downs just because of the system has to be stabilized. So these potentials are known as the hyperpolarizing after potential. So you have a negative hyper polarizing potentials, and there is also something called depolarizing after potentials. So there are multiple cycles of hyperpolarizing or repolarizing and depolarizing hyperpotentials, and finally it comes to the rest point. Again, if you are going to stimulate the muscle, what happen, the next action potentials will be generated if the amount of current is, the stimulating current is well above or is above the threshold limit. And in general we can see that the resting potential is somewhere around minus 60 to minus 100 millivolt, minus 60 to minus 100 millivolt, whereas the action potential is between plus 20 to plus 40 millivolt. Now from the above experiment, the following important observations are noted. Number one, the action potentials are non-linear, which means there is no linear relationship between the stimulating current and the action potential. If the stimulus current is reduced below the threshold, or it is well below the threshold, then no action potential occurs. Conversely, if the stimulus current is much above the threshold, the action potential deflection remains largely unchanged. So irrespective of the stimulating current, once it increase the level, irrespective of the action, what you call the stimulating current, action potential will be generated, which means that once the threshold, once the stimulating current amount which exceeds the threshold, whatever the stimulating current value, but the resultant action potential shape, the shape of the wave, is more or less same. Now for this reason, the action potential is also called all or none. All or none means either there is the action potential or there is no action potential. So all happen when the amount is well above the threshold, and no action potential when it is below the threshold. The action potential waveform remains unchanged at the higher level of threshold stimulus amplitude. So irrespective of the current, once it is crossed the threshold, there must be an action potential. The threshold of action potential is roughly inversely proportional to square root of the fiber diameter. So if you are considering muscle fibers, the threshold depends on inversely proportional to the square root of the fiber diameter. So the meaning is excitation of the median fiber occurs first with a lower stimulus, because since it is inversely proportional, a fiber with large diameter have less threshold, and a fiber with less diameter has higher threshold. So if you apply the stimulating current, then a fiber having lower diameter will stimulate first. Sorry, the larger diameter will stimulate first as compared to the one with smaller diameter. So when the stimulus magnitude increases, it will eventually be large enough to activate both median and lateral fibrils. So here the meaning of the lateral means what? Having smaller diameters. Median means having the higher diameters. So larger diameter will stimulate first, followed by the fibers having lower diameters. Thus, there will be two or more action potentials. Then one more important thing is the velocity of the propagation within each fiber is proportional to square of its diameter. So there are two relations here. One is like the threshold. Threshold is inversely proportional to square root of the fiber diameter, whereas the velocity of the propagation, the signal propagation, that is proportional to square root of its diameter. So these are the two important relations with respect to the diameter. So larger the diameter, lesser would be the velocity, and vice versa. Now there is one of the important equation that we have to use for finding the resting and action potential. It's called the Coleman-Hodgkin-Katz equation. In short, we can say GHK equation. Using this equation, we can calculate the resting as well as action potential. And according to GHK equation, Vm, the transmembrane potential, is calculated by the equation RT bar F ln of Pk times Ke plus Pna times Na plus Pcl times Cli divided by Pk times Ki, Pna times Ni, Pcl times Cle. So here the term Pk stands for the permeability. So this equation is based on the permeability, and Ke stands for the extracellular positive potassium concentration. Here Pna stands for the permeability of sodium, Na stands for the extracellular concentration of sodium. Pcl, again, it is the permeability of Cl, and Cli means it is the concentration of intracellular chloride ions. So just remember, in the case of potassium and sodium, we are using external or extracellular and extracellular. But in the case of PCl, I mean in the case of Cl chloride, we are using I with respect to E. So just because of the fact that the valence is -1 in this case. So this is supposed to be Cli and this is Cle. In all other cases, it is all II. So please note this particular important point. Okay, now how to calculate this permeability? The permeability, that is depends upon dV by d into B divided by d, where capital D is the diffusion coefficient, already we have discussed, and B is the partition coefficient, again it is a constant, and small d is the thickness of the membrane. And as usual, RT bar F we are assuming is that it is 26 milli. Now let us try to solve one problem to using the GHK equation. So find the resting and action potential for an aplysia, which is a sea slug species, from the data given. So different ions are given. I mean ionic ions are given because potassium, sodium, and chloride. Intracellular concentrations and extracellular concentrations also given. And these are just for the sake of understanding the different Nernst potential. As we already know that at resting conditions, the potassium and sodium Nernst potentials are negative, and sodium is normally positive. And here also given Pk, Pna, PCl. These are the permeabilities on a relative scale, 1, 0.04 and 0.45. So it's like a ratios, So Pk with respect to Pk, Pna with respect to Pna, and so on. So this is like a ratio of Pk is to Pna is to Pcl. So 1 is to 0.04 is to 0.45. This is in the case of membrane when it is at rest condition. Pk, Pna, Pcl is 120.45, which is at the action potential. So there are the two different instances the permeabilities are given. So you can see that in the case of resting and action potential, we can find the value of pk and the PLA. PCl is same, but the major differences happen for the Na, sodium. So this is like a case, just for the sake of problem solving, just we are considering here. In natural, I mean the actual scenarios, maybe the situation may be different, the values probably different. So let us try to find out the value here. So step one is we have to find out the resting potential. So as we know, the resting potential is characterized by the equation 26 milli ln of pkke plus pna NaE plus PCl and CLI divided by PKKI plus PNA NIE plus PCl into CLE. So if we substitute all this value, then we'll find that the resting potential is somewhere around minus 58 millivolt. Similarly, we can substitute the second value, as we know, the second case where we have 120 and 0.45. So 120 and 0.45, if we substitute instead of these resting values, corresponding resting values, we'll find the value somewhere around 45 millivolt. So we can see that the resting potential is minus 58 millivolt for this particular Aplysia cell, and the action potential is somewhere around 45 millivolt. So this is like a negative potential which is resting, and the action potential peak is somewhere around 45 millivolt. Okay, so thank you for listening this particular lecture. If you have any doubts, you can discuss now.